Okay. Hello, everybody. So, last week, what did we do last week? Actually, okay. So, yes. So last week we talked about some mathy stuff, but essentially the conclusion was that we could at this point even conclude that we are dealing with non-classical theory, that is theory that's not uni-trajectory theory, because quantum mechanics turns out to be bi-trajectory theory. So rather than having one trajectory representing some observable in the system, we have a pair of trajectories that are distributed according to certain complex value measure on the space of bi-trajectories. Okay, and having realized that, I mean, this kind of makes sense, maybe. I mean, if you think about it long enough, it kind of makes sense that we go from one trajectory to two trajectories. But that's not enough if you want to have a proper complete formalism for theory, because just knowing that this is the underlying structure, that's not enough, because you still have to have some ability, have a power to actually model things. So you don't, knowing that there is some distribution underneath for a pair of trajectories is not enough. You want to be able to actually dissect it into pieces and maybe even figure out some laws according to which you could just postulate new systems for which you would have the distribution then and stuff like that. So we went to the next step was to figure out this dissection. Okay, what are the building blocks, elemental building blocks of this formalism based on bi-trajectory picture? Now, and we started by observing that the bi-probability distributions, those complex, so bi-probability distributions, you can think of them as a discrete time restriction of this bi-trajectory distribution. And those guys, the functions Q, they have a natural connection with inner products on Hilbert spaces. Okay, because they essentially, you have Q, function Q, you can like immediately represent it as a inner product on certain Hilbert space. Actually, on many different Hilbert spaces, there is some ambiguity there. But also we have Hilbert space with inner product. You can like, this inner product can be a basis to create the some bi-probability distribution. Okay, so it's like deeply rooted mathematical connection. But from our point of view, the thing we want to get from it is that there is a Hilbert spaces, structures on Hilbert spaces are probably the way to go if you want to look inside bi-probabilities. Okay, so that was the game plan. And what we started doing at the very end of the previous lecture, we went to trying to establish the famous measurement projector link, which anyone who is familiar with standard quantum mechanics understand this, right? That there's measurements are somehow connected with the action of projection operator on some Hilbert space, right? So we want to establish that thing here. And to do that, if bi-probability works as a inner product in Hilbert space, so in particular, single time n=1 bi-probability is also one of those, also have one of those representations. And so we did that. We said, okay, let's consider we have a probability, there was some initialization parameterized with this distribution P. We talked about it, what it means some previous lectures, and there was a perfectly fine-grained observable measured at time t1 with a result k1, and this probability, is a diagonal part of bi-probability according to our rules we've established so far. And this bi-probability, right, it has this inner product representation, Hilbert space representation, which can be written in this nice trace form, okay? Right, and we identified here it's a trace over Hilbert space, which we label with the chosen observable K for now, because we just keep, we don't know what depends on what yet, right? So we just keep it safe. Let's keep all the indices inside just to
So is it so that at this moment we say that Hilbert spaces may depend on a kind of observable you want to measure actually?
Yeah, it might be. Yeah.
Well, maybe it makes sense because even in the standard approach, probably I think sometimes could truncate your Hilbert space. And for some observables, it doesn't change a thing. You have some spatial distribution of atoms, for example, in Hilbert space, but you want to measure, for example, just a collective spin, then you completely can get rid of many degrees of freedom actually.
Yeah, I mean,
and still your total spin operator will work the same.
Yeah, so our job will be right now, because now it's like if everything depends on everything, right? On every choice of timings, of observables, of initialization, stuff like that, that's not really helpful. So our job will be now to harness, leverage the phenomenological observations we have, pepper in some philosophical considerations, and to curtail the chaos, okay? To make our ambiguity, cut down ambiguity as much as we can, okay? To make something that has a much simpler structure, okay? So we can actually do something with it, establish some laws. That's what we will be trying to do. But at this point, we just, we have just one data point. We have this trace formula. So we according to the stuff we talked about previously, so we have this positive semi-definite operator here, which is called metric, because it is a metric of the implied inner product. We keep all the dependencies here. We don't know what's really matters for it, and we picked some arbitrary bases in our Hilbert space, also picked arbitrarily, right? And this elements of this basis, projections on elements of this basis will connect to the results obtained in the measurement. So yeah. It's okay. Okay, no question. I looked at you and I thought there was a question. Okay, okay, all right. That's why it looked like you have some objection. So let me at this point, because this is a lot to write, this ket-bra, okay? Ket-bra notation. So let me, if we are sitting in this HK, which we picked, the first Hilbert space we picked. Let me use a shorthand notation for projection operators. So small pi, all the indices, of course, right? Projection operator, because it's idempotent, yeah, and it spans the space, right? When you sum over stuff. So that's our input number one. Right. Okay. So now let's consider again the same system. Imagine it's the same system, the same initialization, same timings. But now let us measure, deploy a coarse grain version of our observable K. So K bar. Okay. So again, the probability it's a diagonal part of single time bi-probability, corresponding bi-probability, for which we can again do our trick with Hilbert space representation, and we get again trace formula. But this is different observable. So we pick different Hilbert space K bar. We pick a basis. All the indices are in. Even let's use different letter phi instead of psi. So it's a projector in this rank 1 projector in the space K bar. Okay, and we have metric, corresponding metric. We also have in this space. In this new space depends on the choices and stuff like that. And you can even notice that since K bar is coarse-grained version of K, the dimension of the Hilbert space, which is related to how many different results you can get in your measurement. So dimension of this K bar has to be smaller than dimension of K. Okay. So that's one observation. And now there is another thing that we can tie those things together with, because we have phenomenology. Okay, we know from phenomenology that when you do the measurement with coarse-grained device, only a single measurement, so then you have that this probability decomposes into a sum of classical like behavior with probabilities of fine-grained measurements. This works for the very last measurement, right? If it was some sequence of measurements and you did this for a mid-sequence, right? We have interference, right? So this sum wouldn't work, right? You would have pairwise interference instead. But it's the late, because there is only one measurement, so we are always doing the last one. It's just a sum. But if we have this also tells us that if we go to our Hilbert space representations, sorry, let's write coarse-grained first. Right, this also means that the same relation we have for our Hilbert space representations, right? T1, T0 equals, and the right-hand side, so we have trace K, so in bigger Hilbert space, and here we can write then K1 in omega K1 bar. Oh, argument here would be nice. Pi Kp T1, T0, K1. And the metric. All right. So now we can make some choices. Okay. On the purely logical level, mathematical level, there is no reason to make any connections between Hilbert space K bar and Hilbert space K and the elements inside. The only thing is that once you multiply everything and you take traces, you must satisfy this phenomenological law here. That's okay. But the fact that we have, we are talking about the same system that was prepared in the same way, the initialization was the same, and we are even measuring the same observable, but with just different graining, right? Different resolution. And that just seems very silly to make, those pieces live in different Hilbert spaces. It's just uneconomical, right? So we can come in here and make a choice, like Occam razor type of decision here. Let's curtail the number of entities in our formalism. Let us force them to both things live in the same Hilbert space. Okay, which is our choice. We can try to do that. And of course, we have to we have to choose the larger Hilbert space as our the thing we want to transport everything into, or we will lose some information, right? If you go to if you want to smash something to smaller Hilbert space, this just doesn't work because it would require to get rid of something, right? So let us try doing that. Let us try to extend the representation of coarse grain measurement into the larger Hilbert space of fine grain measurement. Okay, but this poses a problem because here you have operators that live in smaller Hilbert space, and you want to map them on something in larger Hilbert space. Okay, and that's there are in principle there are infinitely many ways to do that. Okay, but we have to pick something. So my proposition.
Try here to do such a kind of abstraction. So how can I, from something less specific, so from the coarse grain one, how can I abstract into the something more specific? And of course, you can do it in many ways.
Yeah, that's what I'm saying.
I think there should be, well, maybe it's more a belief, but it's belief in something that the world is kind of fixed and invariant in the sense that you, although they are different, you know that you measure coarse grain, and there are different options what it can mean. I should assume that there is some true meaning. So there is one true, let's say, this true fine grain Hilbert space, yeah, which I actually probe, but I don't know that I do.
Yeah, so that's what I'm saying. This is that's why we're trying to do this, okay? But specifics now, okay? How do you actually resolve the concrete problem, right? And maybe you can come up with some really nice argument here, but one I present to you now, and it is an option, okay? This is a fork in the road. You might try do something else, and I can actually. I have some hypotheses that there are different options can also lead to something nice, but it's still untested and it's just in my head. But the thing I'm proposing here is let us do the extension by because we have here we have two pieces here. We have the metric and we have a projector. So let us adopt the rule, a principle, that when we do the extension, we map projector onto projector and metric onto metric. So let's keep the function of elements the same. This is a choice, right? You could try to figure out something else. Okay, but let us try go with this. If we encounter some contradictions, yeah, then that's a signal that we have to change something. So if this is the thing that we are deciding to do, then if this is the choice we are making here, then this would mean that we take our projector in a smaller Hilbert space. Okay, 1 bar. Okay. Okay, 1 bar. And we map it onto a projector in larger space. Okay, 1. So all projectors in this K space will be small phi. That's the same as a projector on the right hand side of our phenomenological law. Oh, that was interesting. Okay. Okay, this might. Well, I'm talking a lot here, but I just want to make sure that all the steps I'm doing are well, exposed, so that if someone has so they are falsifiable. Okay, so if someone has some objections, they will know what to attack, when to attack, and at which point the attack should be made, just to keep ourselves honest. So that's for projector, and then the only thing we can do with metric, let's just assign it to the same metric that we have on the right hand side. Okay. So that would be our simple principle, to conserve, to preserve the function of elements of Hilbert space structures upon the transition, upon the extension to larger Hilbert space. So, okay. Obviously, this assignment doesn't break anything, doesn't break our phenomenological law, right? It will be, everything will be fine here. All right. So we curtail a little bit. So any coarse grain version of K, observable K, we can treat it in the same way. So we covered all the coarse grain versions, okay? So we curtail the chaos a little bit. But next thing we can do, okay, so we dealt with coarse grain. So let us now take L device. Perfectly fine-grained L device. And obviously it's L, so I mean that it's inequivalent to K. It's different observable than K, but also perfectly fine-grained. Okay, and well, you have your probability of measuring. You have some probability L preparation P T1 T0 measuring some L, which there is a corresponding bi-probability L, right? And you have the Hilbert space representation. So you have your trace formula. You have some. You have Hilbert space HL. You have bases and projectors. Let's use letter he. He. What do you say it in? Hi. Kai. Right.
I have to ask one day, Panos, how they really pronounce it, because in English they pronounce Greek letters completely differently.
Yeah.
And I wonder who is closer to truth.
So we have new Hilbert space. We have new bases. We have new projectors. We have new metric. Okay. But if we did our transmutation, our merger of Hilbert spaces for coarse grain observable, which is also it is an observable that is inequivalent to fine-grained K, as we discussed. That's why it can cause interference and stuff like that. So if we want to be consistent with our principle, our Occam-Razor stuff, well, we're still measuring the same system, same physical system, same initials, initialization event, same timings, there's different choice of observable, but still observable that like belongs to the system we are measuring, right? So this should also be, you know, let's merge Hilbert spaces again. Okay, I mean, not merge, let's export everything to the same Hilbert space. You know, let's make this choice again. And again, we can apply the same principle we used previously. So we do this mapping in such a way that the projectors goes to projectors, right? Metric goes to metric. So if we apply it here, then we would take this phi P, T1, T0, L, this guy, or you know what? Let me write it here. And boop, it will go to pi, some rank 1 projector. Rank 1 means that it, you know, it can be decomposed as a ket bra, because it's perfectly fine grained. So it has be the same number of projectors as in case of K, because, you know, this that's the law. And the projector goes to projector, and, you know, so again, metric goes to the original metric as well. We did it for in previous case, so we do it here again. All right. So that we're just consistent with our principle we used previously. Okay. Makes sense, right? And of course, you know, we still have to be careful. I mean, we are still constrained by the need to satisfy the phenomenology. So this have to work. So the original Hilbert space representation, it has to give us the same results as the thing we did here. UKP. That's our constraint through phenomenology. But if this is our constraint, we want it to be satisfied, when then it implies something for us, right? Since the metric is the same as it was in case of K, okay, the same metric, the same Hilbert space, this taking trace. So this means that projectors LP T1, T0, L, where L spans the, you know, the spectrum of observable L. This set cannot be the same as the original set of pi k's. Okay, otherwise you would get the same probabilities, which would, but we assume that L and K are not in equivalent observables, right? So if we want to have inequivalent observables, the set of projectors, orthogonal projectors pi L, has to be different than the set of projectors pi K. That would be our conclusion from this. Okay. And if you encounter now coarse-grained version of L, so we can treat it just like we treated coarse-grained version of K, right? Metric is fixed, the original QK, let's take it, because this is how we started. And the projectors corresponding to L bar would be just the sum of projectors corresponding to L, right? So in this way, we basically covered all the options here, okay? And now we can draw some conclusion, some consequences of our actions. Okay, let's investigate consequences of our action. So some consequences. So since we are, our rule is that you take a metric, each metric, you have your measurement for some observable, right? And every time you basically assign to it the same metric. In our case, it was original QK. But if this is the case, then this means that this metric is independent of the choice of observable, right? If every observable is satisfied by the same operator, that means that this operator is independent of the choice of the observable, right? And by extension, it's also independent of the timing of the measurement, right? It's not dependent on what you are measuring. It also cannot be dependent on when you are doing that. So in other words, our choice to map metric matrix to this one original QK operator basically forced it to be a Hilbert space representation of the initialization event. Because if it's independent of observable and independent of timing, when the measurement was taken, then it's only dependent on the initialization. So in other words, this our principle made us like for every observable f and t1 greater than t0, and f, I mean every f, including our original k, observable, fine-grained observable k, which we started. So metric therefore, this metric matrix is independent of k and of t1. So let's pick a new symbol for it, symbol rho, and let's just leave what it depends on. Okay. And this rho is oh my God, I realize my p and rho are just the same. It's the same.
Exactly.
So it's positive semi-definite, and its trace is 1. Okay, this is what's left, but they are independent of k and p. So that would be 1. So in other words, by the choices we made, the consequence is that this metric rho is the thing that would represent the initialization event. And on the flip side, we have the projectors then, which, they seemingly represent the measurement, right? But the measurement is something that's, the measuring device is deployed by the observer, who is choosing arbitrarily what device to deploy, so what observable to measure, and when to measure, right? So, if we pushed the dependence on initialization onto metric, we can, and we should actually, based on what I just said, get rid of the dependence on the initialization from the projectors, right? Because when you are measuring and what you are measuring shouldn't depend on the choice of initialization, right? So we are splitting essentially what those elements, Hilbert space structures represent, even like from phenomenological point of view, which actually this is how we started, right? We want to preserve the function. Projectors goes to projectors, metric goes to metric. So we are essentially implicitly already said that we are envisioning those two elements having some concrete function. They do something concrete. And we followed our choices, and this is where we are getting. So also for every P, T0 and F and capital F and T1 greater than T0, pi F P T1 T0 F is actually equal to something that depends only on observable and the time. So, you know, it's to celebrate the fact that we curtail the dependence, let's pick a different letter. Like with rho, right? So it's a different letter because, you know, it's a new function, essentially. We realize it's a new function that depends on, yeah. And of course, it's a projector. It is a projector. So you have all the projectory stuff. Delta F of prime, E, F. You have spanning the Hilbert space. F. That's one. Okay. So now we have split the. Oh, and of course, at this point, you can already say that the measurement projector link has been established, right? Because we now just have a deployment of the device corresponds to projection operator. Okay, so this is what traditionally you could call the projector measurement link. So at least in the setting, the context of single measurement, right? We have this link that the deployment of measuring device correspond to action of projection operator. And the final comment is that, you know, since everything now is packed into the same Hilbert space, our original HK, which we chose, you know, arbitrarily in the beginning, there is no longer need to label it with K. Okay, it's just no longer needed. There's no sense because it works for every observable. And so we can get rid of that. And if this is the Hilbert space that works for every measurement, well, then this Hilbert space is essentially a property of the system we are measuring, right? That would be our conclusion. So we can now say that we have HS, the Hilbert space of the system. Okay, so this would be like a property, intrinsic property of the system we are measuring then. Okay, its dimension defines for us what is the perfectly fine measure. What is what is the ultimate resolution your measuring device can get, right? This is the number of the dimension corresponds to the number of possible results of perfectly fine-grained measurements, which is all the perfectly fine-grained measurements have the same number when you're measuring this system. So this is like a property of your system. Fine. Well, I meant to say fine, perfectly fine-grained. That's what. If I said perfectly coarse-grained, I'm sorry. That would be kind of silly. Although we did that. We did extreme coarse grain, which could say perfect. Is it perfect?
It's not also aiming the fine grain structure, right? When you develop your theory.
I mean,
You just try, I mean, the difference between coarse-grained and fine-grained eventually dimension of space.
yeah. It is, I mean, that's, if you only have coarse grain, I mean, if you just only made a coarse grain measurement, it's one type of coarse grain measurement, your conclusion would be that the dimension of your Hilbert space is equal to the number of coarse grain results, which would be, by definition, smaller than the number of fine grain results, right? But as long as you never probe the fine grain,
Fine-grained mechanics, and then we can further reduce to further fine-grained.
you see, we have a test for that. Because if you recall, when you hit the perfectly fine-grained stuff, we made this phenomenological observation that when you're doing a sequential measurements, your probability distribution start to exhibit Markovian property. So we can actually test for if you have reached this limit. Okay, if you still not seeing Markovianity, well, that means okay, so I can go further. There is actually there is a dimension of Hilbert space is actually higher than I'm observing right now. So there is a test for that. Okay, so there is some. You might say that there is some. So this is a property of a system, right? This dimension. All right. So let us now, apropos Markovianity, we can actually now do something with that, because remember, with Markovianity, the observation of Markovianity, the fact that you have this factorization of sequential measurement, the probability factorized, and this was a key thing, and I talk about it a bit because this is what actually allowed us to define what initialization event actually is, right? Because of this property, because of Markovianity, we could actually define initialization as a fine-grained measurement can work as an initialization event, right? So, well, we can use this insight and our newly established information about the structures of Hilbert space representation to actually determine what this rho is. Okay, specifically, we can say what it is. Okay, use. I think I wrote somewhere here which observation we will use. Okay, whatever. Use Markovianity. To figure out what rho P is. And this is a grammatically correct sentence. I doubt that. The idea is that we can let's try to find what this rho is. So and to do it, well, it's not that hard, because let's start with consider an experiment with initialization P KK. If you recall, this PKK probability distribution was because initialization is you pick some perfectly fine-grained device, and you do measurement with it, and you get some results. So peak device capital K, you have some result small k, and this is what counts as an initialization. So now you can have like probability distribution that there is some probability that the device used was the probability of picking certain device and getting certain results. Okay, so just a simple generalization of one specific choice of initialization. But let us pick actually. My eyes glazed over. Okay, let us pick. It's K prime prime. That's actually we pick certain concrete device, and we pick certain concrete result. Right, so it's not a distribution; it's just delta. Okay, and let's use a symbol here for convenience. Okay, so this distribution will be we'll denote it like this. And then from our observations, I wrote it down here, from observation 9 and 11, whatever that is, probably Markovianity and something. I don't know. Oh, I know, no, and then uncertainty. So we have P. No. So this is our initialization, and now let's make the measurement. Let's make it also with the device K. So with this device, and let's make it immediately after the initialization. Okay, so we are doing rapid measurement of the same observable. So we are using here Markovianity and probing uncertainty relation. So we make a measurement with device K with initialization denoted by this delta symbol at T0 plus some delta T, and we take limit delta T goes to 0. Okay. Okay. So this thing is equal to, according to observation 9, a conditional probability conditioned on result K0, which according to observation 11, the uncertainty relations. So we had this correlation function K, which in this case would be just delta. Okay. So this is what we get from our phenomenological observations. But now we can represent it in Hilbert spaces. In Hilbert space rep. This probability initialized this way okay, in Hilbert space representation, that's nothing more than trace over our Hilbert space S. We have projection operator for K, and we have the metric associated to this particular phenomenological initialization. And fine-grained measurement. So this is rank 1. So we can even write it as some ket bra. this projector. So we can even write it like this. To make it really explicit what's going on here. T0. Okay. And this, this is something, and it's equal to delta, K0, okay? According to this. So now, given that rho has to be positive semi-definite and has to have trace 1, there is only one solution to this equation. This all implies that rho K0 T0 is nothing else than P K T0 K0, okay? Or you can use the Ket-Bra notation if you want. Because it's rank 1. Just to underline that this is projector, the same projector you would use for measure to represent measurement, but the measurement has to be perfectly fine-grained, okay? Because this thing works only for perfectly fine-grained devices, okay? And immediately you get that rho associated with distribution P, okay, it's just convex combination of projectors. Oh, and that's just density matrix, right? And that's just density matrix. And now, before we take a couple minutes break and we go further, go to full bit by probabilities, let me make one more observation, which I love very much. I just love this observation. I think Mariusz also has some appreciation to it, at least in their passing, that it's like he knew. So look, we did this whole song and dance, and remember there was a fork in the road, right? This to bring everything into one Hilbert space. That choice, this is a choice. Maybe there's a different choice you can make and still get something productive out of it. But that was one choice. The other one was to make this metric goes to metric, projector goes to projector. So we basically we chose to make a metric to represent initialization and projectors to represent the measurement. Okay, that was a choice. Again, maybe you can do something else, but this is what we did. These are the consequences. But if this is where we stand, okay, so far, well, this means that so every observable corresponds to some projection operators, like set of orthogonal projection operators. But so in principle, it also should be that if you pick any set of projection operators, they should correspond to some measuring device. Okay, this is how modeling works. This is why we are doing this. We made this. There is a relation. Actual physical devices correspond to this in this representation to projection operators. So we have to believe then that set of projectors could be, at least in principle, there should be a way to build devices that would correspond to those projectors. Okay. And now, keeping this in mind, consider the following our first formal statement. So let us write a probability. Do the measurement with observable k. You use the initialization, so you concretely initialization by a measurement with device k as well. At some time t1, initialization time t0. But you know what? Let's make it less indices, t and 0. Okay. For k, which you know in our Hilbert space representation, that would be nothing else than you have projector associated with device k at timing t, result k, and then initialization then is associated with the same k, but at time t0, and result k0. Okay. But let me write it by definition. These are formal statements. I take here, I write something like this, a trick. I'm making a trick here. I'm just following my formal stuff I just developed. So I introduced a new projection operators, but we associated with timing t0. And then, you know, it follows what it represents. Well, it must represent, it must represent a measurement. So I'm writing it like this. Okay. k0, which is some correlation function here. k0. So what I'm saying here is that this KT device, which I just invented, is such a device that when you deploy it immediately after initialization, it gives you same result as if you deployed K device at time t. Right?
But you apply it immediately after. This is evolution of project.
That's yeah. I mean, I just picking what I did here. I took the projector PKT and I relabeled it. That's what I did. I just relabeled it. But when I do this relabeling, I have my connection with projector measurement link, which we established. So I'm saying by relabeling, I'm saying, okay, so this was realized by picking some new device, KT, that was just deployed at immediately after initialization. And we just said that, okay, so they should be, in principle, for every projectors, you should be able to build the device, okay? So I'm saying I can do this because this can be realized, okay? In principle. I mean, I'm doing this because in principle, I believe that it's possible to actually build all this stuff. And this is of course, we understand this. If you know standard quantum mechanics, you immediately notice what's going on here, right? We will, the time, the evolutions, we will get there, okay? The concrete relation between KT and K, this is something we'll investigate shortly on next lecture, actually. But what I want to point to this now is that I use this trick, this formal trick. Oh, I have a trick. I just used my ability to model stuff to essentially eliminate time from the problem, right? Because I said you could either, let dynamics take his course. So you initialize T0, you do measurement with some device at time t. So there is a span of time where we believe dynamics takes place. And now I'm saying, okay, the same thing can be, you can get the same thing by picking just different device and just skip the dynamics completely. So if this is possible, and it is, the context of single measurement is essentially static, quantum statics. Okay, you can absorb the dynamics, the flow of time with clever choices of measuring devices. Okay.
To measure the future already today.
Yeah, I mean the future doesn't matter. Future, past doesn't matter in a sense. Okay. In this context of single measurement, preparation and measurement, it's a static context. Okay. And in this sense, if you are sitting in this static
Yeah.
no, actually not the, but the observables. You just have collection of observables, which are,
Change on this, depend on and they change.
depending which observable you choose, you can like simulate the passage of time by arbitrary amount. Yes. But this is so this is. But also, if this is the case, all the observables dynamics has been like absorbed, eliminated, then the row, the matrix becomes like the master object of the formalism. Okay, because every result of every measure, everything you can phenomenologically observe if you constrain yourself to only single measurement that ends everything, ends experiment, it's all confined, it's all derivable from row. Okay, so you have row, you have everything. So in quantum statics, row, the density matrix is the master object of the formalism. Okay, and soon we will show that it's no longer the case when you consider dynamics, which dynamics is, if, for example, sequential measurements is already a dynamical context where you cannot do this trick where you absorb evolution of time into just clever choice of observable. Okay, so in this one specific context, if you confine everything to single measurement only, row is king, row is everything. But it's also static. It's essentially static scenario. Okay, so it's like hydrostatics. For me, I like this analogy. Hydraulic press. You have state of your system is temperature, volume, pressure is all you need. So in this quantum statics, also state of the system, which is represented by rho, is also everything you need. But this won't be the case if you go to dynamic scenarios. Okay. And like in classical hydrodynamics, when you go from statics to dynamics, description is very much different, right? It's like you have everything just completely different. Okay. So I like this observation, and let's take a couple of minutes break at this point before we go to the next bit. And break. So Mariusz, you came in just in, because I told you this analogy many times, and I thought you liked it. So, I was very proud that you liked it.
No.
Yeah, not you're not in love with it, but you like it.
Yeah. No. You can even convince me.
You can even that's that's enough for me.
Criticizing, you think about you are just hiding this time. This is done that we trick to say that if you have single measurement, it's just equivalent to no evolution at all, except you change the measurement. And then you say, but if you have repeated measurement, it is something different. Then, okay, but then, okay, always you might be criticized. So in order to find something really,
This is true.
I still have to think what to tell people in order to say it is not hiding problems which were in standard formulation of quantum mechanics and renaming them and pretending that there are no problems because you change names and you don't use some controversial words, okay?
Yeah,
that
this
you
is true.
Don't say that after test measurement, this is not the state of the system. Okay, what I like to say that people are not convinced that, okay, talk about what you observe. You don't observe the state of the system, but you observe some result of some measurements. So this is a wrong question to say after this measurement, what was the state of the system? Because it suggests that you want to measure everything. Because if you want to measure one observable, you don't ask what is the state. You ask, if I measure at time t10 something, what will be the result of the measurement at time t1, which is larger than t0, and you will get this correlation, probability of this. You don't ask about the state because you don't measure the state. The state is some, I don't know, giving some objective meaning to something which might be not exist at all.
So I feel this story about statics is kind of, it's a, you can use it to like to Stillman or to like show how the idea that state role is a master object always, where it comes from.
This state,
Yeah.
State, but people can put it because it doesn't hurt much.
Yeah. I mean,
but then another thing that I was missing. Last lecture, you said that if you have started by probability, it somehow immediately induces some Hilbert space. But not quite true, because in order to have this Hilbert space induced by this field, you have to have some Hilbert space. You have to have the baby, you have to have vectors, you have to know how to multiply this vector by a complete number, and the only thing that you do, you introduce different space, in different Hilbert space.
yeah, but it's like
but then you put this Hilbert space by hand into your approach.
yeah. I mean, it's like,
so it's not that it's.
I mean, Hilbert space is a pair, right? It's a pair. It's a vector space and inner product.
And scalar. You have to, inner product.
Yeah.
You have to have vector.
So in this sense,
vector space with the vector, and you have scalar field that you can multiply by vector.
yes. So it induces in this sense that.
And then you have to have norm induced by the scalar.
Yeah. Each scalar product, automatically. I mean, so
I can define.
So it induces Hilbert space in the sense that once
you have Hilbert space,
no. If you have vector space,
vector, okay, you have two vector space.
So you have one half,
okay,
which you can pick, whatever, randomly.
You need only vectors.
Yeah, and then you just endow it with.
This introduces the scalar product in this form.
And of course, you can like now introduce unitary transformation that moves you to another different Hilbert space with different scalar product. And also you could just take your Hilbert space with this Q-induced inner product and just take the vector space and
The question was that it does not force you to have Hilbert space, but
no, it doesn't force.
No, some sense, when you have vector space,
this allows you to.
Having this form, you can introduce the Hilbert space.
Yeah.
Induced by this scalar product.
Yeah. So this is just like a motivation why you look for Hilbert space.
There's no motivation why you have vector space, but whatever, you have to assume that your theory requires.
I mean, if
quantum mechanics.
No, if you have something that can work as an inner product, so you want to product something, vectors, right?
Something to use these tools.
Yes.
I can define the scalar product by looking for vectors that I can
if you have only hammer, everything is a nail, right?
Tam
Yeah, yes,
deska
yes.
i gwóźdź, bo
Yes.
wtedy jest do dupy, jak się ma tylko głowę.
Tak jest, tak jest.
Potrzebne jest tak.
So yeah, so this motivates us to, the alternative would be to just, let's ask one of the axioms. There is Hilbert space. And that's-
Let us assume that there is a vector space.
Yeah, that's
But the vector space is so close to states that you would like to avoid.
Yeah.
It's like that. Yeah, if you say quantum mechanics is that the system is described by some vector in some
Yeah.
space, then
that's already presuming a lot. You presume a lot then.
but that's in fact what you assume.
No.
There are
Look.
some vectors.
I led us. Look, I led us. Look, Marsh, I led us to the point where there is a fork in a row, and we chose to go for Hilbert spaces, but maybe someone else can come up with different choice. So I wanted to show, but you don't have to do this. Maybe you don't have
Yeah,
to.
okay, but if you want to have a link to what is right now, it is nice.
Yeah, I mean, there's
Standard formulation.
it's difficult.
But then introducing vectors, you
It's,
introduce states.
Well, we just we just touched upon it right now, right?
Then you get rid of states finally, but you introduce them.
Well, states. I didn't. I said in quantum statics.
In quantum statics, they are useful.
You have concept of state.
Standard mechanics where measurement were destroying everything.
Yeah, just one measurement. Yeah.
The thing that existed. I have the system, I wait, and I check what I prepared after some time.
Exactly.
I destroyed the system, but I, like the system of flies that go around the lamp. You destroy the flies when you catch it. But you can have another one. When you overdo it, you can make a map where they like to be. And you find that
And you
they
have a
are
bee.
in the lamp. You know the joke.
Yeah. From
pewnego czasu mam takie uczucie, że to śnią. To pan mi to światło, ja nie wiem, co to się światło trafiło.
Okay, so on this humorous aspect, we can end the break because we still have some things to do, so the next step, that was our foot. We put our foot into a door. We have so we developed. So we essentially what we did, we developed a Hilbert space representation for single time bi-probabilities. Okay, that's what we did, and now we want to leverage this, use it as a jump off point to actually get the representation for n time bi-probabilities. Okay, and here will be some. This thing is kind of boring. Okay, what we do, boring. It's just some math. So my idea is I will show you the first step, and on the
last one,
and the rest I will just pull up the PDF of the paper, which are updated recently a bit to update some notation, and just go over, because there will be a lot of writing otherwise. So instead of and there's nothing clever in there. Okay, there is just boring formulas with a lot of indices, and that's just no need to waste our time. And they are long. They are longer and they are useless because they are just used to derive stuff. I mean, yeah. Okay. Yeah, I mean, this is the best way to say this, right?
You can cheat it, you can divide formulas into
Yeah, but this is not
Yeah, we can have a short, we just explain the symbols later.
Okay, so
the things we ask who says that the lecture that speak on simple.
okay, guys, let's focus. Let's focus, because I'm so I'm not super confident we can actually make it to the end. So the way we will do it, let us consider a conditional probability, which we have. I realized this recently. We have our conditional probabilities thanks to the causality, the observation number one. I made some progress there in understanding, starting from not having anything to say. And now I have like, oh my God, so much appreciation to it. I'm at the very least, I will incorporate it into. I will incorporate it into the newer version of the paper we are talking about right now. So we have a conditional probability, F1, conditioned on previous guys, and thanks to the causality, we know that this conditional probability can be expressed as a ratio, n plus 1, PTN.
Vector Tn plus 1 in the lower index.
Oh yeah, sorry. Yeah, sorry. Thank you. So probabilities which are
One.
And also F plus
so probabilities are the diagonals of bi-probabilities, right? So everything can be rewritten in terms of Qs. All right, so formally, this conditional probability is a N1 bi-probability. Single time probability, by probability, or also single time. Right. So we are essentially taking n time by probabilities and like mold them into the scenario we had previous. Okay, so we can use our previous result to go forward. And so, because this is formally indistinguishable from N1 single time by probability, we can have for it the Hilbert space representation. So we can write for it, for this conditional dude. And because I know what I want to get, I will do some notation that takes advantage of me knowing the future, okay? So we have here projector for the measurement at time Tn plus 1. That's standard, and there should be metric here, right? Corresponding to the preparation, initialization. But I will, instead of writing row, I will write here a thing, okay? Because I know what will what will follow. We will write, yeah, this is density matrix, but written in a, if you want it, this is how you would arrive at collapse. If this was your goal. So I write the metric, the density matrix in this form, So this Q is an unnormalized density matrix. So the Q is just positive semi-definite, okay? And I divided it by small q, because this is what gives me the normalization. If you, this is what gives me you can, by using the definition, the bias rule, you can figure out that this gives you the proper normalization. And now we will do a trick. So now we know a couple of things about this formula. For one, this is a probability distribution. So if it's normalized, right? So if I sum over Fn plus 1, it's 1, right? Because it's conditional probability. On the other hand, we have projection operators here. They are complete set of projection operators. So I sum over Fn, and they give me identity, all right? So a completeness relation for projectors, and this is a normalized probability on the other hand. So combining those formulas I wrote here, I can get the following. I can get the following thing. Fn Tn. I don't know how to nicely explain what I'm doing here, so I just write it down. Fn, which is it's also equal to P Fn, right? They are equal things. But this thing, I can write it as sum over Fn plus 1. So I'm using now the essentially the law of total probability. Soon I will switch to PDF. So don't fret. Don't fret. Times Q and so this thing here, yeah. So now I can use my Hilbert space representation. I put in this formula, the denominators cancel, okay? And I enter with the sum under the trace, so I get identity from my projectors. And I get trace Q Fn Tn Fn. This is what I wanted to show. That this metric, pseudo-metric Q, which we introduce, the trace of it is actually what gives me a diagonal part of bi-probability. All right. And now, knowing that this is the form bi-probabilities diagonal part of bi-probability stake, I can again do some reshuffling of our formulas we used so far, and we can get the following recursion. I wrote the recurrence equation, where you have a trace of Q Fn plus 1. So that would be a diagonal part of Q n plus 1 times Q. And from the all combine everything here, you can conclude from this that this equals to P F1 plus 1, Tn plus 1, Fn plus 1, Q shorter, n times. plus 1, sorry, plus 1.
So
Which also, since this is a orthogonal projection operator, it's how you say idempotent, right? So it's also equal to square of itself, and trace is cyclic. So I can like double up on the projector and sandwich the pseudometric with it, which is useful because pseudometric is supposed to be positive, right? And when you take a positive matrix and you sandwich it with projectors, you still get something that's positive. All right. So this is a recurrence equation, right? Because it tells us at least trace of q n plus 1 is like is given in terms of q n, right? N plus 1 in terms of n. So it's a recurrence equation, and you have initial condition. Init cond. Initial condition is how do I write it? Q f1 t1 f1 would be f1 rho e0 some initialization event, and rho t0. Let's give it a decomposition in terms of probability, also rho pk t0 k, right? And so this equation has a solution, most likely not unique solution. So you can think of it as another fork in the road. Maybe you can work with some different solution than what I will give you. But the solution I want to show is a solution. It's Q F N T N F N equal to P F N T N F N, and you have this whole sequence of projectors until you reach T1. Then you have rho in the middle, and you fire up your sequence again, but starting from T1 and ending on Fn. And this is by definition positive. And by definition, it is positive, okay? Because rho is positive, sandwiching in projectors preserves positivity, and you're just sandwiching, blah, 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 blah. Okay? You take trace of this, and this gives you so this is one of the solutions that solves this equation. Maybe there are other ones. Most certainly there are other ones. If you add some traceless operator to Q, it also works. But this is the solution we pick. So taking a trace of this guy gives you a diagonal part of bi-probability. So we have so at this point, we figure out Hilbert space representation for the diagonal of arbitrary bi-probability. And we can also generalize it of diagonal, but this I will give you in a slideshow.
This standard, if you think about the small q as a density matrix, this is just saying how the state evolves.
if you choose to, yeah,
You have this collapse that every P projection is a collapse, and
Yes.
how it is incorporated the dynamics?
Yes.
Doesn't
So-
say it doesn't have this projection, and then you have some
I mean,
projections
yeah,
which are introduced by some kind of measurement.
to make a tangent here, yeah, if you think about standard, because we are, the formula we just obtained, this is like a standard quantum mechanics also gives you the same formula for, because this is what we obtained, right? The probability of sequential measurement, which is for us is a diagonal part of bi-probability, is this trace. And this is what you get in standard quantum mechanics as well. Okay, so we are close. But in standard quantum mechanics, you attach a story to it. I mean, you can attach a story to it that involves collapse, process of collapse. But this is something you don't have to do. Okay.
Yeah, but then there is still question. If you wanted to get this measurement of this projection of the part of quantum mechanics, so how come that having the Italian evolution,
We will.
you are adding something
No, no,
like
we'll.
a jump to your theory,
No,
which is behind quantum
Yeah.
mechanics. You say, but this is observation.
No, that would be that's not. That's more than absurd. This is like, this is what we criticize standard approach for. Okay, this is like over interpretation. But at this point, there is no this is what bi-probability is, discrete time version of it. We know that underneath there is there is this by trajectory distribution. At least we have some inkling that it is there. This is the picture we have right now. Collapse, it's something extra if you want to put it in. And I hope I will demonstrate that putting it in is essentially like getting what we are obtaining here and making it worse. It's just you do extra bits to make it worse. That's I hope I will convince you at the end. But at the moment that we have no notion of collapse, there's no need for it. We just following the by trajectory picture. But okay, so we have this diagonal part. Now we want to generalize it to off diagonal also. And to get off diagonal, the off diagonal thing, we can invoke the inconsistency relation. So inconsistency relation was. So it was this formula that, so you take a probability, n-time probability, and you marginalize in the middle, right? If classical theories, you would get something shorter, so this would be 0. But in quantum mechanics, this is given by, there is a reminder, which is like you take by probability and sum over the off diagonal arguments. Okay, at this point you are marginalizing over. Okay, so you have on left hand side you have two diagonal parts of Q, and on the right hand side you have something that involves off diagonal part, which we can exploit to actually generalize our recently discovered formula. And this is a little bit of writing. You know what? I would just show you the result. Okay. Because, there is you make some observations, this one with, you can put in identity. Identity can be represented as a sum over projectors. Then you get this, so the reminder, which is, Q with off diagonal parts, and you take the difference between marginalized and the one with inserted identities. You rearrange some terms, change the names of variables, and you get a formula that this sum, where everything is diagonal except for J, equals the formula where you have the same sum and you have trace, And at J, you have projectors. On left side, you have projector on Fj plus, on right side, Fj minus. So it's easy to conclude from that therefore, the full representation for bi-probability is a trace. You get a sequence of projectors on the left side of row and on the right side of row, but the difference is that on left side, you now can take this sequence of arguments. On the right side, you can take this sequence, the second sequence of arguments. If it's diagonal, you return to what we had, and that's the representation. Okay. And the row, it can be represented with projectors as well. And this is the this is the full Hilbert space representation for bi-probabilities. We kind of achieved our goal. Still, we don't know dynamics. This next step where we have to figure out the dynamics, because at the moment the projectors are indexed by T, but what is the relation between projectors at different T's, right? This has to be established. And one more observation we can make here, because on previously we talked about, we established the projector measurement link, right? Seemingly in the context of single measurement, the action, the deployment of device is like corresponds to action of projection operator. But this formula, this already demonstrates the limitations of this picture, right? Because now, if you take a sequential measurement, so this is a dynamical situation, not quantum statics, and you just you take our formula which we just established and just use cyclic property of trace to move all the projection operators on one side, and you have here rho, so the state, the initialization event, and you have some, you can just name these guys with some operator E, all right? And in general, this E is not a projector, all right? So in other words, you cannot like absorb it, what's going on here, into a choice of a observable that you deploy immediately after initialization. Unless you extend the notion of observable and you say, oh, E guys, POVMs, but that's just, this is not constructive approach, I would say. If you think about this,
not projective measurement, but positive operator value measure.
Yeah, and then I really don't like this.
Because ER positive.
Yes, ER positive, they sum to 1. Yes, exactly. But this is an extra structure you introduce. And saying now this is more fundamental, I mean, we can have discussion about POVMs. I want to say here that, this guy cannot be absorbed into a measurement as we understand according to what we deduced. This is not K device or F device or any other device we consider so. It is a actually it's not even look, this is a probability. This is not any, this is some completely new device if you want to, because you cannot even decompose it into like a sequence of application of F devices, stuff like that. Because, previously application deployment of single device was projection operator. But this is not a product of projection operators. E is not like some product or sum or something like that of projection operators. It's this. This is a new kind of structure, which doesn't fit into anything we had.
Second term is product of projection operators will die.
Yeah, but they are like, the timings are completely. You cannot disassemble it into like some simple composition of some chronological sequence and stuff like that. So in other words,
Sequence of pairs of projectors.
I mean, if you really want to like do some and claim, but if you want to like claim that this E-POVM, right, is a new fundamental thing, you would do this only to preserve the idea that row is a master object. This is the if you want to
do my best to preserve the idea.
And that's why I don't like this, because this is no, I don't like this approach, because if you consider only measurements, then it kind of works. But beyond that, in complete dynamics, quantum dynamics, which we'll get to what quantum dynamics is in addition to sequential measurements, you would then have to again introduce some new thing, and this new thing would actually be much more interesting quantity than this initial condition row. This initial condition even in this sequential stuff is completely non-interesting. Yeah, I mean that's what I'm saying, okay? Multi-time correlations are the real interesting stuff. And that's dynamics, that's quantum dynamics.
Concept that you substituted the problem of collapse by introducing something external to quantum mechanics like K devices. This is something totally external to formulation. We have such a device that will do this.
No. Look, my program is to model K device inside quantum mechanics, which I believe is possible. It wouldn't be possible in standard quantum formulation. It wouldn't be. And here I think it's very much
Some collapse in projector is something out of the Schrödinger equation and out of the scheme of unitary evolution and everything, and I am adding this extra, and nobody was able to find the model of this extra.
Yeah, exactly. And
my
claim
of unitary evolution, whatever, that
yes.
was the problem. But you just said, okay, I have quantum mechanics, I have this probability that I observe, and I have my devices which make the observation, which are something external. And then
yes, so
the difference is that you are thinking from standard quantum mechanics that you start to formulate it from the very beginning in terms of multi-time correlations like trajectories, which is also recently people think about. Okay, at the very beginning of quantum mechanics, measurement was destroying the system, so nobody was thinking about repeating the measurement on the same system.
Yes.
Now you have possibilities to have some non-destructive measurement, and you think about it. Right. But
exactly.
As long as you will not give example of K device within the quantum mechanics, you are mostly renaming things. No?
I mean, you are partially right that it's.
Yeah, this new language is useful to say.
It's like it's not just renaming, but I agree that our obligation, because we are doing this together. I'm not, you're listening to me. You're not stopping me. Our obligation is to, once we have the ability to make models, to make a model of measuring device.
Yes.
Otherwise, we are just stuck at the same thing. And I think we can do it.
Okay.
And on this happy notion, let us finish.
Okay.